My name is Tobias Schmidbauer, and today I will present you our paper, A Survey of Indirect Network Level Covered Channels. From now on, every time I mention the term covered channel, these are network level covered channels. So first of all, the key contributions to take away from this talk. The first key contribution is an overview over all until now known 37 indirect network level covered channels, further on called ICCs. Second, we introduce a novel taxonomy unifying the domain by grouping all covered channels into 3 patterns, which consist of 2 major patterns. Further, we identified crucial features all covered channels rely on, allowing a more differentiated comparability. And finally, we give an overview over application scenarios and already established and potential countermeasures. So let's talk about the fundamentals. Covered channels in general are policy-breaking communication channels that are not originally foreseen. So they nest into legitimate communication, the so-called overt channel or cover object. Besides some other general differentiations, literature divides the domain into direct and indirect covered channels. As you can see on the left, for a direct covered channel, the covered sender CS and the covered receiver CR communicate directly with each other. Intermediary nodes are not necessary for the covered channel, however they may be essential to establish the overt channel. For the indirect covered channel on the right, an intermediate host has an essential role in the covered communication as the CS and CR rely on the exploitation of the intermediary to communicate with each other. In our paper, we introduce a novel taxonomy, which, as you can see, consists of 2 major patterns, the so-called Redirector and Broker. The Broker further has 2 minor patterns, the Proxy and the dead drop. So, first of all, how can an intermediate host be described itself? It is a crucial system for an indirect network level covered channel that reflects, stores or represents CI, and further it has not necessarily to be aware of being a participant of covered communication. So let's talk about the redirector, which setup you can see right now. The CS manipulates the intermediary redirector to reflect a message to the CR. So the redirector is exploited to redirect covered information, but does not intentionally represent or store the CI. An example is the TCP SYN packet where the sender's IP field is the CR's IP address. So the redirector is forced to respond an acknowledgement to the CR. Now, this is the setup for the proxy, a minor pattern of a broker. A broker performs as a passive actor in an ICC that is manipulated by the CS while the CR has to actively extract information from the system. So there is a manipulation and an extraction. And for the proxy pattern, the CS manipulates the proxy in such way it represents CI, which further can be extracted by the covered receiver by requesting it. A proxy represents covered information but does not store them intentionally. An example you can imagine as an DDoS attack, busying the intermediary and delaying packet response times which can be detected by the CR. Storing CI is a crucial signature of the dead drop pattern on the bottom of the slide, which is also a broker. The CS manipulates the dead drop to store CI, and again, manipulation and extraction are separated. CI now have a lifetime on the intermediary host, so they disappear with time or by an event. Further, the covered receiver can decide when to extract the CI, which leads to a time difference between sending and receiving. An example for such a dead drop can be an ARP request that is stored within the ARP table. This table can then be extracted, for example, with an SNMP request by the covered receiver. Let's talk a little bit more about dead drops. I already mentioned that CI entries are disappearing. We call this effect fading, and there seem to be 2 types. First of all, the logic fading, which is caused by an event, For example, a CI entry is overwritten. And second, there is some fading relying on time. Like, for instance, an entry in a DNS server that after injection is stored for a specific time and then is dropped if it's not renewed. So CI also have a lifetime, and we introduce 3 categories for such a lifetime. Persistent entries rely for longer than an hour on a dead drop, while temporary entries are stored for longer than 1 minute, but less than 1 hour. Volatile entries remain for less than 1 minute and need to be extracted frequently, which on one hand wipes evidence on the dead drop, but might create suspicious network traffic. These are the features ICCs rely on. First of all, the utilized network protocol itself has some features presented on the left. Some protocols have to be violated to exchange information via an intermediary, while others behave conclusive. Also, for some protocols, CI exchange was possible for without authentication on protocol layers, while some forced authentication, and there also exist protocols with optional authentication that can be activated. Further, the reachability is a feature, which means can the protocol be utilized to transport informations to other collision domains. Also, the amount of CI within one transmission attempt, we called bitrate, is a feature, as well as the utilized information hiding patterns that categorize the strategies for information hiding. These hiding patterns were introduced in 2017 and have been revised in 2021 and are beyond the scope of this paper. For this talk, you only have to know that these are unfolding timing and storage-based information hiding strategies. So for the brokers, the manipulation and extraction is separated. 2 protocols have to be described for such an ICC. Further, intermediary brokers have features as they are cover objects for ICCs. For the proxy, the load intensity has been added, and further the proxy itself has an information hiding pattern as presented in the middle. Finally, the dead drop features are presented on the right side. As CI are stored in a cache, this cache has a capacity, the amount of CI it can store. And further, the already explained fading and CI lifetime are features. Finally, also the dead drop implements an information hiding pattern. So enough for the theory. Let's talk about the evaluation. We analyzed all to the best of our knowledge known ICCs. We named them after their protocols and added a number marking their historical appearance and sorted them top down. This table presents all until now known redirectors, and as you can see, there exist frequent MQTT implementations. This protocol by design involves an intermediary for overt communication and has been systematically analyzed for CCs in 2 papers by Velenov et al. And Miliva et al. Let's take a look at the publication years. The first ever described ICC was published in 1997 and founded this research area. You can see most of these channels have been described in recent years, which describes the focus on ICCs that currently appears. So, for the features. Most protocols were not violated and behaved conclusive. And further, no protocol enforced an authentication, while some protocols have optional authentication, which may reduce the number of potential CS and CRs and limit or eliminate the CI exchange if activated. Further, most protocols were able to extract information outside of collision domains. The bitrate varies from some bit to multiple bytes. For the final column, the information hiding patterns, I already mentioned the unfolding of storage and timing strategies. EN and RN represents such a storage strategy, while ET and RT represents timing strategies. This is a very rough summarization, as it is quite complex, but you may have an impression that mostly all known redirector ICCs are based on such a storage strategy. So for the proxies, as you can see, there are fewer implementations than for the redirectors. If we take a look at the publication years, we can see that except one, all proxies have been described within the same paper in 2019, which is also special because the covered channels introduced within this paper can be combined with each other. All proxy ICCs are until now load intensive, which means plenty of requests have to be sent to influence the proxy. Anyhow, we assume that there exist mechanisms to block a crucial resource within fewer requests, allowing a load intensity that is much lower. So we introduced this feature. The information hiding pattern utilized at the proxy rely on the same storage strategy, while the manipulation until now bases on one specific timing pattern and the extraction relies on another specific timing strategy. So manipulation and extraction seem until now to not violate protocols, do not rely on authenticated protocols, and further mostly are not bound to collision domains. The bitrate of all channels is 1 bit for manipulation and extraction. This table presents all known dead drop ICCs. Most of them have been introduced in recent years. So let's take a look at the dead drop features and talk about fading. A filled dot represents timed fading, while the empty dot stands for logic fading. As you can see, currently more dead drop ICCs rely on logic fading triggered by events. The CI lifetime overview presents that almost all combinations are imaginable. Especially for the logic fading, if no frequent events occur, the CS may decide when the CI disappears, like for example for MQTT and ARP. The capacity and bitrate also varies. For the dead drop itself, the capacity depends on the cache implementation, so the number of entries and the values that are stored are crucial. During the manipulation, often small chunks are injected, while for the extraction, it seems like the whole cache is extracted, so the bitrate and the capacity correlate. It seems like never a protocol is violated and that authentication is either not available or optional. Further, all extraction protocols and almost all manipulation protocols are not restricted to collision domains. There are two special ICCs in this table. First of all, MQTT1, which also can be implemented as a redirector, dependent on if the CR joins after or already is connected to the intermediary during the CI injection. Second, the net1 channel, which is special for various reasons. This is NetSpectre, and first, it does not rely on a specific protocol. Second, the level 3 CPU cache is exploited, which is not meant to be a network protocol cache. And third, this might be an ICC performing some type of hybrid fading, which means timed and logic fading are both available for this implementation. However, this was not described in the paper and we did not test it. Let's take a look at the application scenarios. First, the redirector on the left can be used for a simple bounce, but also broadcast and multicast messages are possible. An example, therefore, is IGMP, where multicast packets are utilized to implement a timing covered channel. In the middle, the proxy seems to always be a sort of broadcast channel because all systems that can access the intermediary may extract CI. Further, if the proxy is a physically shared resource, CS and CR may cross logical separated network segments. And finally, for the proxy pattern, protocol switching can be applied, which means manipulation and extraction do not rely on the same protocol. The application scenario for dead drops are presented on the right. First, this pattern allows the separation of the CS and the CR as they can be active at different times. Second, the CS can slowly inject CI, complicating countermeasures. Like for the proxy, protocol switching can be performed. And finally, we also assume logical separation may be crossed by shared caches. However, to the best of our knowledge, this has not yet been described explicitly. So let's switch to countermeasures. Countermeasures against covered channels are performed by wardens that have been introduced by G.C. Simmons. They either can be passive, active, or malicious and may detect, limit, or eliminate the flow of covered information. We have described all potential placements of wardens for ICCs. One placed directly at each actor of the ICC and one located at each connection between the actors. The wardens were numbered from 1 to 5. These are the countermeasures we found in the surveyed papers and additional warden publications. Most of them have been evaluated for specific ICCs, and some of them are potential countermeasures we additionally described for the context of ICCs. So, as redirectors sometimes rely on protocol violation, this might be detected by all wardens. Examples may be packet acknowledgements without a SYN package, which can be eliminated by the wardens number 4 and 5. Further, an increased occurrence of events may also enable a detection as well as inter-packet gaps. Most of the presented countermeasures can be implemented at all warden positions. For the proxy, the manipulation bursts are noisy and may lead to a detection at warden number 2. Warden number 3 may detect anomalies at the intermediary system. And furthermore, proxy CCs rely on timing and packet delay. This may be detected at warden number 4 and 5, and the CI exchange can be limited or eliminated by applying normalization and randomization of response times. Dead drops may be detected by cache observation at warden number 3. This warden may also apply a shared resource matrix to determine which participants can read and write specific resources. Further, especially the extraction may be detected as large amounts of CI are extracted at once, causing anomalies detectable by wardens number 4 and 5. Warden 3 can finally limit or eliminate dead drop ICCs by limiting the cache size to a necessary minimum or flushing caches regularly, destroying the CI. So let's talk about future developments within this research area. First of all, and most obvious, we expect the expansion of ICC patterns to other network protocols and network environments. Especially IPv6, VoIP and IoT networks and protocols may be interesting, but also low-level protocols like Bluetooth may be exploited. Further, we expect the exploitation of specialized network devices, printers for instance, and non-network caches for dead drops, like shown in NetSpectre. Next, as already mentioned, there is potential to exploit the proxy pattern without high load. And likewise also mentioned are hybrid fading dead drops. And finally, some sort of hybrid class covered channels may exist. We found one paper exploiting Dropbox functionalities to transport CI. The covered channel was not implemented within network protocols, but this points at a direction we might observe highly sophisticated indirect network level covered channels, also exploiting cloud services and operating systems resources like storage, for example. So finally, our conclusion. Indirect network level covered channels are an emerging topic within recent years. We were able to group all existing ICCs in 3 patterns which allow better analyzation. Further, all ICCs relied on repeating features that make these indirect covered channels comparable within the pattern group. There are currently only used a subset of information hiding patterns for such channels. For example, proxy patterns rely on 2 very specific information hiding patterns. We also conclude that however countermeasures may exist, these have not been evaluated and investigated for ICCs. And finally, we identified various future developments within the research area, pointing out the potential of such channels. So thank you for your attention. I'm looking forward to answering your questions about our research.